Welcome to Privacy Vault for PII data, a unique solution for privacy-preserved processing of PII data using cryptographic computing. PII data needs to be protected in all three states: at rest, in motion, and in use against attackers both from inside and outside. The problem of protecting PII data at rest and in motion is solved through different types of encryption. However, protecting PII data while in use or in process is still a huge challenge globally. The reason all current databases are designed to process data in plain text form. Therefore, irrespective of encryption used at rest and in motion, data has to be decrypted to plain text form for use by the database. This gap is the biggest vulnerability for organizations and biggest opportunity for hackers. A lot of work is happening globally to process PII data in encrypted form without decrypting. There are two approaches mainly categorized as hardware-based and software-based. In software-based approach, we have fully homomorphic encryption, zero knowledge proof, secure multi-party computation, differential privacy are some of the approaches. All of them use their own methods of cryptographic computing. At Posidex, we have invented another method of cryptographic computing called hashcryption, combination of hashing and encryption. We de-identify PII data, rendering it useless for attackers while maintaining usability and referential integrity for data processes, applications, and services. All PII data elements, names, dates, IDs, etc. are converted to irreversible tokens through a 5-step process: vectorized, encoded, anonymized, randomized, encryption, VER token. These tokens are used in computation through proprietary mathematical equations. Plain PII values are never used in computation. In this demonstration, we will showcase how Privacy Vault compares two types of PII data elements, names and dates, with fuzzy search capability. Users can dynamically adjust match thresholds where fuzzy search is required. The user provides two identical names, Chen-Long and Chen-Long, as input. Initially, VEA token is generated, vectorization, encoding, and anonymization, an irreversible hashed token. Then randomization with the salt key followed by AES 256 encryption is applied, creating a VER token. The final output is a unique combination of hashing and encryption known as probabilistic hashcryption. Now, plaintext values are discarded. Comparison happens on the two hashcryption tokens. Since the names were identical, the tokens match 100%. Now, we introduce a slight variation in one of the names and generate new tokens. Let's compare Chen-Long and Chen-Long. Even with this small change, we observe a significant variation in the generated VEA token. Next, VER token is generated. We now drop the plain text and compare the hashcryption values. Using our fuzzy matching algorithm, the system calculates a similarity score of 89%, demonstrating fuzzy search capability on tokens. Just like with names, we can also compare two dates. The hashed token generated for dates is entirely different from the one generated for names, ensuring data type specific security. This is called polymorphic tokenization, applying different tokenization and comparison methods for parameters like names, dates, and identifiers. Finally, we drop the plain text and compare the two dates securely, ensuring accurate and privacy-first data processing. Now, two dates are given where there is a date and month interchange. VER tokenization is done. Even though the dates are different, still they match with 95% similarity. This demonstrates fuzzy search on dates. Likewise, mistakes in year or within a date range are also supported. Our approach, enabling exact and fuzzy search on irreversible tokens of all PII data elements at the same time maintaining usability and referential integrity makes us a unique solution globally.